Omnidirectional 3D information is essential for a wide range of applications such as autonomous driving, virtual reality, and scene reconstruction. To obtain omnidirectional 3D data, LiDAR devices are commonly used. However, LiDAR scanners are very expensive. On the contrary, regular cameras as well as 360 cameras are much cheaper. If we can generate good quality 3D information from regular or 360 RGB images, the cost can be largely reduced. In order to capture an omnidirectional scene, multiple scans are required for a regular camera due to its limited field of view, while a 360 camera has a much larger field of view. One scan is sufficient to cover the entire scene. If we can infer depth from a single 360 image, the hardware cost can be greatly reduced, as one scan can recover a complete 3D scene. To recover 3D information from 360 monocular input, existing methods often use a single deep neural network to directly learn the mapping between RGB and depth. Various depth-related cues, such as shape, lighting, and object type, etc., are implicitly learned during training. On the other hand, stereo matching methods explicitly learn the appearance correspondences between stereo pairs. We can achieve robust training and better performance if stereo geometric constraints are given. Stereo methods, however, require at least a pair of images as input. So can we use this when we only have a single input image? How about we synthesize novel views from the monocular input first, and then apply stereo matching on the new images together with the original one. Through this, we can leverage the stereo constraints to provide geometric guidance to the network for a more accurate depth estimation. We, for the first time in 360 vision, propose to formulate 360 monocular depth estimation as a two-stage problem, including view synthesis and stereo matching. First, we pass a 360 monocular input into the view synthesis stage, where one or more novel views are synthesized. Next, the original view and the synthesized views are used together as the input to the stereo matching stage, which outputs a final, high-quality depth map. Our approach, PanoDepth, is model agnostic. In other words, the networks in the two stages are replaceable. With our customizations for 360 domains, such as spherical warping layers, PanoDepth outperforms previous state-of-the-art 360 monocular depth estimation approaches, regardless of the combination of network settings. In the view synthesis stage, we use a monocular depth estimation network to produce a coarse depth prediction from the 360 monocular input image. We then use a differentiable depth image-based rendering module to synthesize novel views based on the coarse depth prediction. Here we will show some examples of our qualitative comparisons with current state-of-the-arts. In these examples, we can see that our PanoDepth recovers more details of the scene. As highlighted in the red box, we can observe that PanoDepth recovers clear shapes of the objects on the table. The predicted depth maps from PanoDepth also maintain sharper edges, such as the pillows on the bed as highlighted. PanoDepth also predicts the depth accurately with less artifacts. We also conduct generalization testing to see how well our PanoDepth generalizes, especially on real-world datasets. We train the model on 360D and test the model on a different real-world dataset, Laval, which does not have ground truth depth. As we can see, our method can recover the indoor structures more accurately comparing to the current state-of-the-art. More specifically, in this example, we can see that our estimated model has all 4 straight walls and sharp edges, while the current state-of-the-art failed. Here is another example of the generalization testing. Our PanoDepth can handle the narrow and long corridor with correct scale than the current state-of-the-art. Here, we show some quantitative comparison results. Our method outperforms the state-of-the-art by a large margin. For example, PanoDepth achieves at least a 19.6% error reduction in terms of absolute relative error on the Stanford 2D/3D dataset, and 25.8% error reduction on the 360D dataset. In this paper, we, for the first time in 360 vision, propose a novel two-stage end-to-end framework PanoDepth. consisting of view synthesis and multi-view stereo matching stages. Experiments on multiple benchmark datasets show our PanoDepth significantly outperforms the current state-of-the-arts.